Today in this video, we'll discuss the combination of capacitors. Now you know already the combination of resistors. If resistors are connected in series, either in series or parallel, the equivalent resistance or the net resistance in the circuit you can calculate with different parallel and series combination formula. Now what about the capacitor in series and parallel combination of capacitor? If many numbers of capacitors are there, then what will be the when they are in the circuit, then what will be the result, right? What will be the equivalent capacitance or the net capacitance of the circuit? So to solve all these things, first the basic two combinations we will discuss. The first combination we will discuss, that is the series combination. So if capacitors are connected in series like this, right? So what will be the net or the equivalent capacitance? Now, as we know that if capacitors are provided a potential difference, then one side will be plus Q and another side will be minus charges will be accumulated, which will be minus Q. Now, the net charge of the capacitor is 0. So from the conductor, the charge will start flowing to and it will be accumulated plus charge in opposite plates. So a plus Q amount of charge will be accumulated, and here a minus Q amount of charge will be accumulated. This will be valid for n number of capacitors connected in series. If I'll connect another third one also, same Q, plus Q and minus Q will be accumulated over that capacitor. So we can extend this combination to n numbers of capacitors, either series or parallel, no issue. So we have taken first the two capacitors. Now each capacitor here, let's say, is having capacitance C1, here capacitance C2. Two capacitors are there. Now we know that if capacitors are there, then each one will have some potential difference. Let's say capacitor 1 have the potential difference, potential drop V1, and capacitor 2 will have the potential drop V2. Now the net potential drop which is provided by the source voltage, that is, let's say V, and it should be V should be equal to V1 plus V2. Now the basic definition of capacitor says us that the capacitance C equal to Q upon V, right? So here let's say your C1 equal to same charge is there on both the capacitors, so Q will be there, but denominator it's V1, and C2 will be Q by V2. Now instead of V1, what I can write this is Q by C1, because V1 is just cross multiply you have to. So Q by C1 is your V1. So similarly, this will be Q by C2, right? So this is your V. If I'll take Q common, it will be V by Q, which will be 1 by C1 plus 1 by C2. Now you see that V by Q is the total charge or net charge of your combination, and V is the net for V voltage. V is the net or total voltage provided to the capacitors. So V by Q will be basically Q by V is your C, the combination of capacitor, that is equivalent capacitance, or you can say V by Q will be 1 by C equivalent, basically. Like you know, the resistors in parallel, equivalent resistance 1 by R equal to 1 by R1 plus 1 by R2. So similarly, just opposite, if you want to remember this, that combination of capacitor series is just reverse of the resistor. The resistor parallel combination is 1 by R1 equal 1 by R equivalent equal to 1 by R1 plus 1 by R2. Here in series combination it is 1 by C1. So V by Q will be basically 1 by C equivalent combination or equivalent capacitor equal to 1 by C1 plus 1 by C2. Now instead of here we have taken two capacitor first. Instead of two capacitor, you can take n number of capacitor. So for n number of capacitor, your net for n number of capacitor, n capacitor Your 1 by C equivalent will be 1 by C1 plus 1 by C2 plus dot 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 dot. It will be 1 by Cn, n number of capacitor. So this is the combination of capacitor in series. Now let us discuss for the parallel case. So for parallel case, let us connect this capacitor in parallel. So parallel means both the terminals of this capacitor should be joined to the single. So they are now in parallel combination. Now we will provide a potential difference V to the capacitors, and each one having capacitor, let's say C1 and C2. Now as they are in parallel, so the voltage, both the capacitor will receive the same voltage. There will be the potential drop for each capacitor will be here also V volt, here also V volt. Remember, this is the difference between series and combination. In series, each capacitor was involved with a potential drop V1, V2, but here same voltage both the capacitors are getting. So here V and B, but the charges accumulated on the capacitor plate will depends upon the capacitance, so it will not be same. So here let's say plus charges are accumulated, and let's say this is plus Q is accumulated, Q1, and this will be minus Q1, negative charges are there, the amount of charges, but we cannot, the charges accumulated on the capacitor C2 will not be same like Q1, it will be, let's say, Q2. The charges accumulated over C2 will be different from capacitor 1. Let's say this is minus charges, so minus Q1, Q2. Right, the net charge here, the logic will use that the net charge supplied by the source voltage will equal to the number of, because here division is there, charge actually like Kirchhoff's law, the current gets divided. So in branching here the charge gets divided, right? The charge is, current is basically the flow of charge. So here the charge gets divided in parallel combination. So the net charge provided by the source voltage V will be divided into two, Q1 and Q2. So the logic will use that Q is the total charge provided equal to Q1 plus Q2. So we'll begin with this logic. And Q1 will again use our basic form definition of capacitor, that C is equal to Q by V. Here V is same for both the capacitor, Q is different. So C1 equal to basically Q1 by V, and C2 is equal to Q2 by V in this condition in the parallel case. And we can write that here Q1 equal to C1V and Q2 equal to C2V. So here from this definition of a capacitor, that we got Q1 equal to C1V. If we use here Q1 equal to C1V plus C2V equal to your Q, and Q also you can write this is CV. C is the C equivalent or C net capacitance, and V is the potential provided. V equal to C1V plus C2V. Now C equivalent will be this, all this V will be cancelled, C1 plus C2. So this is only for two capacitor. Remember, for parallel, if resistors are connected in parallel, then your result is 1 by R equivalent equal to 1 by R1 plus 1 by R2, if you remember. But here in this case of parallel, when the capacitors are connected parallelly, the equivalent capacitance is C1 plus C2, like your series case in resistors. So this is the difference, and you should know, remember that capacitor and resistor series and parallel combination, the results are just reverse, right? So here two capacitor, it is C1 plus C2. If we will take n capacitors, in parallel, n capacitors in parallel, then your C equivalent in the circuit, it will be C1 plus C2 plus C3 dot, 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 up to Cn number. So this is parallel and series combination of your parallel and series combination of the capacitors, the results we have discussed in detail. Now let us discuss one question. So let us solve the equation. Question is that four capacitors are in a circuit oriented in this way. You are providing a potential difference V to the circuit, and each capacitance value, your, let's say this is C1, 2, 3, C4, each value is 10 microfarad. The question is, what is the net capacitance in the circuit and the charge on each capacitor? Let us first only discuss about what is the net capacitance of the circuit. So the net capacitance, here you can see the C1, C2 and C3 are in series. If you look at the junction point, then from the junction all the three are connected in series. So C1, C2, C2, C3, they are in series. So we'll use the series formula, that 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3. So here the 1 by 10 plus 1 by 10 plus 1 by 10. Basically this is 3 by 10. So C equivalent equal to, just reverse, 1 by C equivalent equal to 3 by 10. So C equivalent will be 10 by 3, 10 by 3 microfarad. The unit will be microfarad. Now the fourth capacitor C4, which is having the same value also 10 microfarad, this will be, now we can this will be parallel to all the three capacitors, because all the three capacitor we can replace them with a 10 by 3 microfarad capacitor. The equivalent capacitor we have calculated. So instead of 3 capacitor, if we'll use 10 by 3 microfarad 1 capacitor, then that is also same as using this 3 capacitor. Now you can see that this equivalent capacitor and C4 are in parallel. So we'll use the C net or net capacitance C equal to your C equivalent plus C4. So C equivalent we got 10 by 3, C4 is 10. So this is basically 10 plus 30 by 3. This is 40 by 3 microfarad. So net capacitance of this circuit is 40 by 3 microfarad. Now we can also calculate the charge. We'll not do in this video, we'll do it in the later. We'll also solve few questions, some more circuits in the problem solving section in the coming videos. Thank you.